So I'm considering a problem of basically a one-shot secure source coding problem here. Um, so we have an encoder A and a decoder B that we get to design, and we want to transmit a random variable, a discrete random variable x losslessly to the decoder. And there's an adversarial eavesdropper here who gets to view this public communication M and produce its action Z. And the way we formulate the problem of secure communication is as a game being played between the communication system and the adversary. And so the precise objective that we care about is so there's an arbitrary real valued payoff function pi which takes as input the data x and the adversary's action z. And so basically we want to maximize the worst case average payoff. So we pick A and B first, and we release it to the adversary, and then it the eavesdropper can do whatever is optimal for it. And so this departs from popular approach to secrecy, which is complete independence between the data x and the message, known as perfect secrecy. The point being that perfect independence might be more than what is required in practice. So just want to draw attention to previous work that was done out of our group, where basically an asymptotic version of this problem was considered, where block coding is allowed. It's no longer one-shot communication. And a notable feature of this setup was what we call causal disclosure of information to the adversary. What this means is that at time I, when the adversary produces zi, it gets to see both the message m and all the previous xi minus 1 symbols. And so note that this causal disclosure assumption might seem a bit unnatural, and indeed, if you remove this causal disclosure assumption, with or without causal disclosure, for n equals 1, the problem boils down to the one-shot problem. However, it turns out that it's only with the causal disclosure assumption that the trade-offs you get in the asymptotic regime are relevant to the zero delay problem as well. And so this was solved by Cuff and Schiller in previous work, where so there is a rate region which specifies a trade-off between communication rate, secret key rate, and the optimal payoff. And it turns out that if you remove this causal disclosure assumption, you get a trivial rate requirement. Any arbitrarily small secret key rate will suffice to give you maximal secrecy. That's maximum payoff in this game. So I guess I have two sort of regimes I consider in this poster in terms of code design. So one is where we restrict the communication to be efficient. That is, the number of messages must be equal to the number of values that the source X can take on. And we want to ask the question, what is the most efficient code to maximize this average payoff. And so this turns out to be purely combinatorial problem, where we have this graphical representation of codes where basically the red lines indicate the encoding when the key bit. I'm sorry. So to simplify, we're also considering only one bit of secret key here, which is it's still it still gets sophisticated even with one bit of secret key. So here the red line is the encoding when the key bit is 0, and the black line is the encoding when key bit is 1. And so you can see that with this graphical representation, or you can translate this to representation in the form of permutation cycles on the alphabet. And it turns out you can come up with a linear time dynamical program to find the optimal code that maximizes the payoff in this game. So I guess I'll skip through the details here. So along with Hamming distortion as a choice of payoff, we also considered log loss, which is a popular choice of payoff in the information theoretic secrecy community. In particular, in the asymptotic version of the problem, this leads to a quantity known as equivocation, which has been the subject of study starting with Weiner's treatment of the wiretap channel problem. And so even for the log loss, we have a dynamic program to solve this combinatorial optimization problem. We can construct the optimal code under the constraint that communication has to be optimal. um, so um, so here's another aspect of our work is basically, we asked the question, what if we relax the efficient communication assumption? Can any overhead in communication lead to potential gains in secrecy? And it turns out, somewhat surprisingly, that it can. So in particular, using randomness, local randomness at the encoder can help to maximize your payoff in this game. And the idea is quite simple, actually. So basically, using randomness at the encoder allows you to split up source probabilities in a way such that the posterior distribution of the eavesdropper, given the message it observes, is always uniform, which, for most, well, reasonable secrecy metrics will sort of maximize secrecy. So in particular for Hamming distortion and for log loss, which leads to the conditional entropy, you know, uh, uniform posterior distribution is optimal. And so finally, basically the point of this part of the poster is that you can achieve the asymptotic rate region with zero delay stochastic encoding by time sharing at most two memoryless encoding systems. So yeah, I think that's sort of overview of this work. Thanks.